Donc, the early stages of category theory, 1945-1971, in philosophical perspective. This conference has two philosophical aims. First of all, analyzing the ways in which were created some contemporary and actually new mathematical concepts and objects. Then depicting the outstanding epistemological explanatory capacity of category theory. It is therefore devoted to the first developments of category theory from 1945's Islanders and MacLean foundational paper, hereafter EM45, to MacLean's epoch-making treatise, Categories for the Working Mathematician, which he conceived as a summa aimed at a larger audience than the categorist. Forthcoming in the second half of 20th century, category theory involved a specific shift in the modes of mathematical thought. Rather unexpected, in my opinion, if one recalls the mathematicians' concerns in the 1920s or 1930s. As everybody knows, categories are nowadays in use, at least as a frame of thought, in a wide range of mathematics, a fact which was hardly conceivable 30 years ago and turned out to be an authentic conceptual revolution. As one of the obvious primitive origins, but at one only, the success proceeds partly from a new kind of symbolic writing resting on diagrams. This point was clearly emphasized by MacLean. It was actually a new kind of symbolic writing, actually the first one which succeeded since the 17th century. Inside diagrams, and much more inside commutative diagrams, one can find many implicit informations which could not be recovered without cumbersome computations. Actually, it is mostly an impossible method. Categorical diagrams, however, which can enter a syntax, be handled, substituted, or concatenated, are not an abbreviative system, but a symbolic one. This is an important epistemological distinction. Let us also stress this point. The arrows, they lie at the core of the diagrams, appears only recently. MacLean remarks that the discovery of the use of the arrows in the 1940s, was a conclusive element for the constitution of the theory. C'est une citation qui a été déjà donnée hier par Charles Aluni. Thus, a notation, the arrow, led to a concept, category. And further, the use of these notational devices, c'est toujours MacLean qui parle, preceded the definition of a category. I suggest that this, MacLean speaking, I suggest that this precedence was a necessary first step. Preceded by some general historical and epistemological remarks, the present paper distinguishes 5 main phases in the development of the theory for the current period. First of all, you can read with me universality and naturality. Second, first steps of the decontextualization process, and so on. Two outstanding interpretation optional means if I have time enough. It means outstanding interpretation category being used as a mean of interpretation some previous well-known mathematical results. First section is the historical context of the birth of the theory. The first is directly, and it is well known, and historically linked to some homological questions on which were working MacLean, Eilenberg, and Steenrode in the 40s. The other comes rather under a conceptual filiation and must be found in the work of Marshall Stone on the representation of Boolean algebra in the 1935s. 2 papers profoundly homological of Eilenberg and MacLean. The first, Group Extension and Homology, EM42, hereafter. The second, General Theory of Natural Equivalences are associated to the beginnings of the theory, the second being usually identified as the official birth certificate. The initial task for the authors was a description in the best way possible of the mechanism of some homological theorems, quite easy to understand, but rather puzzling to describe and to represent, that is difficult to communicate. Hence, at the time of building the theory, the ontological question was certainly a subordinate preoccupation. The diagram was some kind of a shortcut or a draft, which could, for instance, explain to the reader homomorphisms between group extensions, as well as universal coefficient theorem, UCT, linking homology and cohomology groups. This theorem, one of the direct origins of the theory, was at the time an important result which determined, with inverted commas, the cohomology groups of a chain complex with respect to an arbitrary abelian discrete group G in terms of its integral homology groups at h and xn of G. Definition and properties of group extension, as well as the proof of UCT, were previously widely studied in EM42. It was a time, however, as MacLean remarks, when the mathematicians really needed a simple and coherent explicative system, since no arrowed scheme for an exact sequence, nor general, nor even short, was available. At the time of EM42, the authors had therefore no other solution than to describe rhetorically the properties, kernel and range, for instance, of each homomorphisms involved between the groups of the sequence, and especially quotient groups. A clumsy procedure which will be simply avoided using a linear arrowed diagram. And actually, EM45 started by providing diagrams with arrows of the short exact sequence, which you can read behind me. However, this diagram was not enough for the following computation, since in the sequence, one had moreover to allow a variation for k. And this variation was obviously dependent from the nature of K, a chain complex, that is a family of three discrete abelian groups together with a family delta exponent Q of group homomorphisms, such that more or less delta exponent 2 equal to 0. On the other hand, any legitimate variation of K was the result of an arbitrary chain transformation F. For any two given chain complexes, K and K prime, the chain transformation is a family, in turn, of group homomorphisms commuting with the boundaries. Actually, there were a lot of hypotheses and parameters involved. Yet, from an abstract viewpoint, it was not completely impossible to express them traditionally, that is, with symbolic writing. However, it would have resulted considerable practical problems for their representation. When one actually reaches this level of complexity, what had been considered so far as a question of degree, that is, the number of representations to take into account, turns out to be a question of nature. This was a key point. In other words, how to depict adequately the shift of an exact short sequence under an homomorphism affecting its chain complexes. For solution, EM45 produced the first plain commutative diagram in the history, so no longer a linear one. One must note that the mapping F star induced by F acts in the reverse direction. From then on, one could describe what happened if for J given and K variable, first for the group H and X n minus 1 of K and so on, then X, then finally H exponent n, under the shift induced by the chain transformation. One recognized, actually, very simple schemes of thought. This is MacLean, the second section. What is mean is that for J fixed, each exponent n of bar and G is a functor of K. This functor turns each chain complex into an abelian group, the cohomology, and so on. This was certainly a characteristical except of the first categorical style of the time, of the 1945s. Thus, by the simple formula, gamma equal to x of K and J, the functorial writing allowed the possibility of capturing the concepts of variables and functions applied to structures, which was never done before. And this was the keystone of the success, coextensive to the status of the letter in mathematical symbolic writing. Actually, if within the range of previous mathematical symbolic writing, the idea of conceiving K as a sign of some variable and X as one of a function matched some spontaneous conceptions of the mathematicians, one must ask the reasons why they did not do so before. One then brings to light two obstacles. The first is a theoretical one, required along this line to exhibit some universe where K could vary, and so involve interdictions associated to such expression as the set of all chain transformations, coextensive to the set of all groups, or the set of all sets. The other obstacle, a practical one, required to specify the legitimate modalities of variation for K, and the correlative modalities for the image X of K of J and J. As we saw, category theory answered directly to the second objection. K must vary only according to chain transformation, which is not so simple an object. And the functor X must take into account jointly objects and arrows. As to the first objection, an ontological one, it was not actually a worry, at least at the beginning, for MacLean and Eilenberg as firm pragmatists. Next section is devoted to functors. Category theory therefore considers objects and arrows altogether, simul in actu, without any provisional nor theoretical anteriority. For instance, as it is well known, sets and mappings or topological spaces and continuous mapping. This is exactly the role of a functor, whose action must not restrict to one of these entities only, which would have been classically the objects, but both at the same time. This conception is indeed a dynamic one, by which transforms by the single actions objects and relation between them. MacLean, while criticizing later some pervasive set theoretical conception, as he told, will propose categorical viewpoints as representing an opposite, non-Platonician vision of the mathematical world. In a well-known text from 1970 on the influence of Marshall Stone on the origins of category theory, MacLean dates back the early foundation, this is the second historical origin, dates back the early foundation of category theory to Stone's conception on the representation of Boolean algebra and the quite new relation between algebra and topology which Stone displayed. Suppose that to any given Boolean algebra B, one associates the compact topological space E equal to spectrum of B, that is, the set of all its prime ideal with the suitable topology on it. And if B is legitimately shifted, what does it mean? If B is subject to a Boolean homomorphism to be prime, then one has, on the one hand, E equal to spectrum of B and E prime equal to spectrum of B prime. And the question of Stone was, what is the relation between E and E prime? If we note E prime is equal to H star, E equal to H star of E prime. And Stone's, this is an actual question of Stone, an important mode of thinking which is going all through his work. And Stones answered with the words of the time. Each star is a continuous mapping. Well, and later on, MacLean will summarize his own answer by describing spectrum as a contravariant factor from Boole, the category of Boolean algebra with Boolean homomorphism as arrows, to top, the category of topological spaces with continuous mappings. Yet, I go on with speaking with functors. Yet solidarity between objects and operations in the conception of a structure was previously stated, but it was in a rather abstract and implicit way, as did universal algebra theory. Universal algebra was created by Birkhoff and Orr. So that the new theory will be the first to take it conveniently into account. For instance, a group must not, categorically speaking, be considered, as in universal algebra, as an underlying set supplemented with algebraic properties, but rather as a package deal, made up with a structure and all its relation with the outside group word, that is, the morphism of which it is the domain of the codomain. This point was completely shadowed in universal algebra. It was not a logical fault in universal algebra. This solidarity between object and arrows will even involve an unexpected dissymmetry. Arrows are actually much more significant than objects, since, as it is well known, one can build a category from a proper axiomatics on arrows only. That was, for instance, Ehresmann's approach in category structure, whose specific work was remarkable with respect to this point. The new theory relativized also the canonical dissymmetry objects arrows, since one of these essential issues rested on the consideration of functors as the object of a new category of functor. In such category, the objects are thus functors, while arrows are the natural transformation between two of these. In the next section, one sketches some basic properties of diagrams: composability, transitivity, associativity, commutativity, universality. They own different epistemological status. Composability is actually the necessary condition of every existence in category theory. Once it is satisfied, transitivity and associativity are valid and then necessary in an arbitrary diagram. Quite the opposite, commutativity is contingent. I shall speak a few more words about composability and transitivity. In order that the arrow fg exists, it is necessary and sufficient that domain of f equal to codomain of g. This is a condition of composability. In such case, hgf equal to hgf as soon as both composites do exist. This is associativity. These different steps are carefully distinguished and analyzed by Ehresmann, for instance. Composability transitivity is a very usual mechanism in mathematics with various instances within the scheme of the middle term. In order that one can simply put together two objects, it is necessary that there exists a common middle term, here, the domain of G equal to codomain of F. Afterwards, and as soon as this consistent condition is fulfilled, some compound object, fruit of the gathering, is produced by forgetting the middle term. Therefore, the existence as well as the essence of the new object are both made up with the forgetting of what precisely allowed its production. For instance, rule of index chain in matrix products, or formation of the syllogism, which must forget the middle term. Transitivity, inherited from composition from mappings and transitivity of binary relations, belongs consubstantially to the definition of any category. MacLane emphasized how much the lack of this property as a fundamental piece in the definition of Birkhoff and Orr made a significant difference with category theory. Though it was actually not a logical mistake, it explained, according to MacLane, is explained partly the unsuccess of universal algebra theory to describe adequately the landscape of mathematical structures. C'était un moment, il y a eu un moment où la théorie des algèbres universelles a pu sembler à un certain nombre de chercheurs comme étant la solution qui permettait de décrire les structures. Le terme de structure a d'abord signifié étymologiquement treillis, puisque le treillis des sous-structures. Bon, I go on with English. Commutativity, on the contrary, Lowther prefers interchangeability, is doubtlessly contingent. A categorical diagram need not be commutative, but the definition of concepts which are interesting and fruitful are precisely those who make a diagram commutative. One is therefore led to new diagrammatic forms of thought. In the basic case of a square diagram, you can imagine of the square diagram, commutativity means, roughly speaking, that two parameters are available, displaying two ways for reaching one and the same result when fixing one of the parameters and allowing variation for the other. The commutativity of the diagram then expresses the fact that the order of obtention is indifferent. Well, it is clear that when restricted to the simple square case, this indifference property could be expressed with mathematical classical terms, that is, symbolic writing. But using of diagrams makes proof and concepts illuminating according to MacLane's favorite terminology, since they turn out to be a guide for thought. But this is not enough, of course. Above all, many more sophisticated diagrams are evidently available, and indeed are used, made up, for instance, by the concatenation of a finite or infinite number of such square diagrams, or triangular or trapezoidal, for which one could not, in practice, express commutativity algebraically. There are numerous examples of concepts created by commutativity. Very often, this is a way of creating new concepts, very often completed by universality, a subsequent property from which one may usually get unicity up to isomorphism. Next section is devoted to consistence and concrete instances of category theory. One can understand from the excerpt of EM45, which I gave before, that what were actually Eilenberg's and MacLane's initial preoccupations, and they were not existential. The primitive pragmatism of the approach excluded, at least at the beginnings, any actual insistence about ontological inquiries on statements about of category of all sets and all groups or all categories. The authors of EM45 freed themselves soon from any such constraint. Later on, in the category for the working mathematician, CW for hereafter, in the CW of 1971, published at the time of the first maturity of the theory, MacLane could not accept this situation any longer. And in the book, actually, the paradoxes of set theory were evoked, but at the same time, circumvented and solved, with inverted commas, by postulating the existence of some Grothendieck universe U. Clearly, this part was, MacLane borrowed a emprunté ce changement de position au SGA, au début du SGA, qui, lui, est tout à fait correct sur le plan de la définition des univers. Bon. In this condition, by definition, I just give a few details on Grothendieck universe. By definition, I said solved by postulating the existence of some big enough Grothendieck universe endowed with some precise closure properties. By definition, the elements of U were called small sets. In these conditions, small mappings were to act between small sets. From which it followed the definition of the category set of small set, then GFP of groups whose underlying sets are small, and so on. Well, it is clear that the pioneers did not worry very much about the ontological question. On the other hand, this initial pragmatism involved, obviously, that the mathematician had to take for granted as part of a given universe all the previously existing, with inverted comma, existing structures, algebraic ones as well as topological ones, and moreover, relation between them, and finally, networks of such structures. Thus, an image new at the time, we have some, it's rather difficult for us to understand this. Thus, an image new at the time of some pre-existing mathematical landscape made with structures and interconnections emerged for the theory. This practice was repeatedly supported by a constant aim to extract general mechanisms from various constructions. I will speak of this later on. Yet, when publishing this early conclusion, the authors did not bring any new mathematical result in their first papers. MacLean himself emphasized the fact. Actually, they did nothing but reformulate some known results and exported them into universal frames of which they were simple instances. For professional mathematicians, indeed, this approach had to be considered at the time as an epistemological commentary. However, with a specific, I should say, a specific genetic flavor, or as a pedagogical essay, irrelevant anyway to the field of mathematical research. Recall that, rightly, the scientific community always thought necessary to make a distinction between science and reflection on science. It was, however, a very special type of commentary, since written within a mathematical apparatus with new and special signs, arrows and diagrams, and not within the natural language as one would expect for an epistemological text. Thus, one can better appreciate the early qualification of general abstract nonsense, which Steenrode granted initially the new theory. Therefore, the matter could have rested there, and the theory be extincted, as it happens rather often. As MacLean remarks, neither him nor his co-author did think that their paper could raise any mathematical research effort. It's written in proper terms. And he went on thinking so until the discovery of adjoint functors in 1958, a decisive step. Afterwards, things did really change. I shall speak now of concrete, this is the best word I could find. Recall that, historically speaking, the conclusive initial motivation was homological, mainly chain complexes and Church homology. That is, a rather sophisticated technical object. But afterwards, once the central concepts of category, functor, and natural transformation were drawn up from this technical instance, and this very technicity might have legitimated the authors for creating a new theory. Si à partir d'exemples très simples et immédiats, ça décourage l'inventivité, il n'aurait pas été nécessaire de fabriquer une théorie. Most of the examples which were used and still in use as conceptual supports in various categorical definitions happen to deviate from the initial homological machinery and turn out to be much more simple. The paradox is that the axiomatics of a category which arose from the homological context was actually poorly restrictive. Second point, various instances of concrete category were first used as conceptual supports by the pioneers. This is an important point. At the first stages, one of the main concrete instances was doubtlessly sets, the category of all set of all small sets. Its arrows are simply the small mappings, and this is a category which is a central one, the role of which will be, especially after Lovier's work, unceasingly a subject of interrogation for categorists. Which is the role of sets in the construction of category theory? Do sets necessarily come before the definition of category as one usually believed? Or is it possible to succeed to set freeing by a suitable axiomatization? Is it possible to, another question, is it possible to characterize set theory itself by purely categorical means, that is, without any reference to membership? Well, doubtlessly, I shall answer to this question later. Doubtlessly, many of the first new general definitions, this is also an important point, epimonic equalizer, subobject, injective object, projective object, were first imported from sets, then tested over it, before being abstractly extended, if possible, to some other categories. For instance, the definition of an epimorphism was a result of decontextualization in an arbitrary category of the basic set theoretical concept of subjectivity. This is I shall say, it's difficult to say decontextualization in English. I should say in French better, decontextualisation. So I shall say for sure decontexting. This is set freeing. The second step was more algebraic. The categories involved were mainly GRP, the category of all small groups, and also AB, the category of abelian groups, and R mod, and so on. These instances and their specificity will serve on turn as support for new types of algebraic abstract definitions, becoming models for the construction of additive and abelian categories. This aspect was, as to my knowledge, first studied by Grothendieck, and he was followed by Fried. There always was another model. I'm looking for describing concrete category as serving support for the thought and support for constructing abstract concepts. So there was always another model for early categorical thought of a very different species, simply a preordered, a preordered set, that is E, P, comma, inférieur ou égal, considered as a category per se by itself. Here the objects need not be thought of as big. That is, unlike the previous examples, they are not themselves usually structures or sets, but simple elements of a single element E. One can remark here a gap between levels in size. And there is an arrow in P from A to B if and only if A is less than B or equal. Transitivity is therefore translated by associativity, so that between any two elements there exists at most one arrow. In other words, the preordered category represents some specific binary relation underlying to any category. It may be thought of as a skeleton of categorical organization. This instance, which was not at all a trivial one, was present from the very beginning in EM 45 under the name of quasi-ordered sets. And on the other hand, the set omega of X of all the open sets of some topological space X is obviously a basic example of such preordered sets. Recall their future constant categorical use in sheaf theory. Another limit example, in a direction, however, completely opposite to the latter, was simply the category group G. In this case, there is but one object, some group G, while the arrows are the element of the group, composition of arrows corresponding to the group operation. Next section is natural transformation, for short in NT. It was actually the first phase. The concept appears from the beginnings, EM 45, and the authors found it crucial. They even explained that the definition of categories was actually inessential. As they wrote, they built up the theory just in order to give a suitable theoretical frame to functors and natural transformation. Here's a quotation from EM45 and later on from Peter Fried in his book 1964, Abelian Categories. Well, the scheme of a natural transformation involves a pair of functors. I shall try to give a summary. The scheme of a natural transformation involves a pair of functors f and g, both between two given categories C and D. A natural transformation between two functors, then, is a correspondence n which associates to every object A of C one arrow n of E of D from f of E to j of E, such that for every arrow j in the initial category C, the following diagram of D is commutative, and we get relation indexed 1. So, if we restrict for the moment to technicity, in technical terms, naturality depicts, therefore, what must become legitimately inside the terminal category an arrow of the initial category under the action of the two concerned functors. But this technical explanation is not an explanation at all. Actually, there are two viewpoints and two terminology as well, yet logically equivalent, but epistemologically distinct, by which one can interpret the concept of Tn. The first is more epistemological and philosophical and mostly American viewpoint, for instance, EM45. The second one is more algebraic and deals with morphisme functorial or functorial morphism, as in Grothendieck, Ehresmann, and Poitou. In EM45, NT are directly, this is the first viewpoint, are directly associated to schemes of universal construction in the extent that they are the proof of their universality. Roughly speaking, a construction is universal if it is made in the same way for all objects and all arrows. It will not, therefore, be enough, for instance, to prove that some objectal formula remain unchanged, an opinion which a primitive but usual superficial coming from set theoretical viewpoints could have prompted to believe. One will have, moreover, to prove that it is transformed in a similar way by similar transformation. Universal, thus, is opposed to specific. Defined, therefore, in this way, a universal construction goes beyond the contingency and the specificity of an object or a process to find out some permanence. From the beginning, an aim of the authors at the very origin of category theory was to give an accurate mathematical signification to the word similar, and not to be satisfied with the imprecise formulation above. So, a natural transformation, or equivalence, captures mathematically a certain concept of universal construction, which is a philosophical concept. In order to show the permanent essence, well, how to do? In order to show the permanent essence of the same process, the method usually takes any two distinct occurrences of the result. In order to prove, perhaps not they are equal, they need not be, but that the transformation from one to the other shows an invariable inner structure. This is the core of naturality. With respect to the second, we speak now of the second interpretation. With respect to the second interpretation, algebraic, NT have an essential structural place in categorical organization. They are morphism between functors. From a philosophical viewpoint, there is therefore a quite different approach. Thus, within the range of category theory, natural transformation correspond to an abstract conceptualization of a second level. First, categories with their object and morphism, then categories of functors whose objects are functors, and morphism, natural transformation. In EM45, si je pouvais avoir un truc pour écrire, non? In EM45, the authors propose many examples of natural transformation for functors. Oui, c'est tout, c'est juste un tout petit peu. Voilà, ça va. Ok, c'est bon, c'est bon. In EM45, as I told, the authors propose many examples of natural transformation for functor or B or multifunctor. In the first section, they try to capture what they call the character, natural or not, of a construction of structures, the keystone of the paper. To do this, they make use of an example, counter-example, endowed with much rhetorical value, which is the example of dual and bidual of a finite dimensional vector space over some field K. Any such vector space V is then isomorphic to its dual V star and therefore to its bidual V star star. But these isomorphisms are epistemologically different. The first is not intrinsic, since in order to construct an isomorphism between V and V star, one must actually choose a basis for V. Therefore, concludes EM45, this isomorphism, V isomorphic to V star, is not natural. Quite the opposite, as to the isomorphism between V and V star star, the formula. Qu'est-ce que je fais de ça? X chapeau of f equal to f of x, valid for every x in V and every f in V star, so shows that x chapeau is actually linear, as well as the mapping x gives x chapeau, so that the formula finally builds an isomorphism from V onto V star, a procedure which one can believe fall under an abstract general mechanism. But this was to be proved. Actually, in order to prove the universal character of the construction of the bidual, the authors will show that it results from a natural transformation. So they had to produce two functors and a correspondence. This is easy to do. The two functors are identity functors for the one and functors star star, bar star star for the second, and the correspondence. Well, I should stress the fact that to prove naturality, one had to follow a very specific scheme. So, EM45, as I told, this example of the dual and the bidual is a rhetorical example. One can find it in Freud's first pages of his book also. At the end, EM45 proposes yet more simple examples. For instance, the canonical homeomorphism. The canonical homomorphism between any three topological spaces is viewed as a comparison of the value of the object functions of three functors, right and left in the formula. Actually, this formula must be understood as the commutativity of the diagram of natural transformation which I gave before. That's the method. A lot of usual identities, bijection homomorphism, may therefore be reinterpreted under this process. Such results, however, might appear a bit slender. The first non-trivial example of natural transformations happens further in EM45. It is, of course, homological. No, I won't give it. I shall finally sketch another example of natural transformation, simple but not trivial. Actually, it is a transformation, not an equivalence, which MacLean gave later on. the construction of a determinant of a square matrix with elements in a commutative unital ring. One must prove that the construction is universal, and in fine, one has the diagram. Then the correspondence is an NT before the two sentences. This proves in MacLean viewpoints that the construction of the determinant is a universal construction. Next step is devoted to products and coproducts and duality. Next step was MacLean's work. First, within the specific frame of group theory. In Duality for Groups, 1950, he explained the purely categorical construction in GRP of the direct product and the free product of two groups, G1 and G2. First, direct product. Roughly speaking, the direct product is such that every pair of morphisms towards the factors can be uniquely extended to a morphism towards the product. One then formulates a problem and draws a diagram. Let G1 and G2 be any two objects of GRP. One seeks a triple, gamma P1, P2, composed with an object and two arrows, and the arrows must be thought of as projection, such that for every object G prime of GRP and every pair of arrows there exists exactly one arrow such that the following diagram is commutative. Recall all arrows here are morphism of group. As an immediate solution, one can take gamma equal to G1 cross G2, direct product, and for P1 and P2 the actual projection of G1 cross G2 on G1 and G2 respectively. First of all, some remarks. First of all, the previous one does not define but one object. However, it is easy to show that any two objects, gamma and gamma prime, satisfying the requisites are pairwise isomorphic, hence to the direct product. It follows that gamma is defined only to up to an isomorphism of the category. Second remark, the above definition overlooks, that is ignores, the element of the underlying sets. It considers but the objects that are groups and the arrows morphism of groups in GRP. Third remark, from then on, it can be then exported as such, that is categorically towards any other category, hence providing in sets the construction of the Cartesian products of two sets, in Delard the construction of the direct product of two distributive lattices. It follows that the general definition of the product of two elements in an arbitrary category, if it exists, and all the category which I quoted previously admit such finite products. Afterward, the paper stresses this important fact. To simply reverse the direction of the arrows on the diagram yields a fruitful another set of problems, namely the existence of the free product of two groups. In this case, every pair of morphisms from the factors can be uniquely extended to a morphism from the product. This is the dual problem. And in this case, an obvious solution takes gamma prime equal to the free product G1 star G2 and G1 and J1 and J2, the inclusions that are the canonical injections. Existence and unicity of H come from the very definition of a free group. Since it is got by reversing the direction of arrows in a commutative diagram, the definition of gamma prime is a dual of gamma. Hence, one will from now prefer the general term of coproduct instead of free product. One has the same remark. The definition of coproduct, if it exists, can also be extended to any category if it exists. It is unique up to an isomorphism. 3. The definition ignores the elements of the underlying sets, that a category may possess finite products and or coproducts was from then a recurrent question. As to the category pre-order, for instance, the existence of the product or coproduct corresponds to that of the least greater bound, or respectively, greatest lower bound. It follows that a lattice is obviously the only such category with finite products and coproducts. Later on, the concept of products and coproduct were subsumed under more general concept. Repeat. Applied to a concrete category, that is, for instance, GRP or sets, this definition overlooks the elements of the underlying sets, since they consider the sets per se by themselves. This was at the origin of the first reflection of Lovier in 1963 thesis about the axiomatization of the category of sets, ETCS, Elementary Theory of Category of Sets. One must stress MacLean's evolution on this point, his primitive incredulity about Lovier's proposition, doing sets without elements, a position which he will soon give up towards his much more thoughtful and supported with arguments declaration about the structural deficiency and the conceptual inadequacy of set theory to represent the modern mathematical world. This is a reference to a discussion on paper from MacLean on ground set theory, theoretic foundation. On the other hand, the process of reversing the arrows in the diagrams, which was highlighted, can be substantially considered as a meta-method, the so-called duality, able to create in a blind fashion, that is, without thinking of it, a new mathematical concept. If one considers but structural viewpoints, duality belongs to the intimate nature of mathematical thought. This was the underlying philosophical position. Later on, though, MacLean would restrict in some way this opinion. Next section is Lovier and ETCS. Next phase was the result of what I could call an accident d'histoire. The meeting between a pragmatist, MacLean, and a visionary, which is Lovier, which in my opinion was an important element for the development of mathematics in the late 20th century. One analyzed below an important paper, 1964, of Lovier, summarizing the conclusion of his doctoral thesis, which was a cornerstone for the mathematicians of the time in their inner representations of categories. It ended on some unprecedented developments of the theory itself. The question was, according actually a completely new approach, an attempt of axiomatizing the category of sets, that is, identifying the specificity as a category of sets, hence distinguished, for instance, from GRP. Here's Lower's quotation. This first attempt was followed by many others and was one of the origin of conceptualization of toposes. As was the ultimate desired conclusion being the final replacement of set theoretic by topos theoretic. The approach was new, since set theory was considered so far as a whole frame of reference for thought, in which, for instance, were potentially contained all sets of issues about groups considered as sets with an additional structure. But Lovier considered set theoretic conceptualization itself as a simple category, even though it was an important one. Thus, as a first conclusion, Lovier's approach weakened the universal referential position endowed so far by set theory, but above all, axiomatizing within the categorical frame made necessary decontexting or desubstantializing the basic set theoretic concept, which had to be, therefore, previously carefully analyzed in order to extract their categorical substance. Yet this attempt was foreseen before by MacLean, as I told, product and coproduct, and above all by Grothendieck and Soutruc in Tohoku paper of 1957. However, in the present case, the whole set theory was involved. It was actually an outstanding attempt, a change of paradigm. MacLean wrote afterwards that he firstly believed it an impossible task. Lowe succeeded, however, in this paper to desubstantialize a simple concept as elements, inclusion, subset, membership, existence of sequence, or the exponential b exponent a. Note that b exponent a involves the existence of the power set. Desubstantializing was for Lowe within the categorical context, defining set theoretic concepts irrelevantly to any membership dialectic, that is, the dialectic between set and element. This approach was followed by other works from Lowe and others. But, however, it was not the first. I repeat, in his Tohoku paper 1957, Grothendieck was doubtlessly the first to desubstantialize the concept of subset under the name of Soutruc. Lowe, for his part, while keeping the frame of the first order logic, but adding 8 axioms to the axiomatic of a category which was then classical, succeeded specifying set theory as a category. Let us finally, a side remark, stress axiom 5 as axiom of choice, whose independence with respect to the other axioms turned out to be trivial within this frame, within this set of axioms. Next section is adjunctions. Daniel Kahn's creation of adjoint functors in 1958 was the decisive step for the emancipation process to establish category theory as an autonomous field. MacLean used to note that in his opinion, without the discovery of adjoint functors, category theory would not have known any proper development and stayed, I quote, a language and an orientation. The two steps scheme of the discovery by Kahn is close to the 1942-1945 in 2 steps as well. As MacLean in the beginning, Kahn worked in homology on simplicial complexes, a subject on which he recently published a paper. To clarify his developments, he was led to introduce new categorical concepts and finally to publish in 1958 a purely categorical, reasonably long paper, 37 pages, Adjoint Functors. Kahn showed a noteworthy virtuosity with respect to categorical concepts, especially natural transformation. The beginning of his paper explains that some types of relations between functors are usual, so that one must try to decontextualize the situation. Adjointness concerns, as I suppose everybody knows, but adjointness concerns 2 functors f and g operating between any 2 categories in opposite direction. F is, say, left adjoint for g and so on. One of the first important results stated by Kahn is if f possesses an adjoint, right, for instance, it is unique up to a natural equivalence, that is isomorphism. In other words, adjoints, if they exist, go by pair. What is remarkable in the so-called adjunction scheme is the simultaneous process of building up 2 antagonist functors, yet closely linked, however, without requiring between them any kind of bijection, equivalence, or isomorphism. One could describe this ancient figure of thought, namely equivalent thought, between entities or structures, as made up with 2 antagonist processes, the successive execution of which leads to identity, whichever the direction of effectuation. And it had directed, actually, mathematical thought from Leibniz to Cantor. Cardinality arises from equipotence. This form of thought by equivalence, from this kind, de ce schéma de pensée, de cette figure de pensée par équivalence, naît le concept d'invariant. Et donc on peut trouver donc par exemple chez Cantor de l'équipotence émerge la cardinalité, de l'isomorphisme ensemble ordonné émerge l'ordinalité, etc. C'était donc une figure de pensée qui était répandue. Bon. EM 45 itself went on trying to enforce this ancient conception, since it is entitled A Theory of Natural Equivalences and not Transformation. On the contrary, one of the major interests of Kant's concept was weakening the figure so that mathematicians can free from it. Well, I shall give three well-known examples, and it would be. First of all, the well-known forgetful factor from AB, Abelian group, to sets. For instance, it forgets group structure and conserves as objects the underlying sets only, and as arrow the underlying maps instead of group homomorphism. Obviously, this factor cannot be thought of as injective. Various elements of AB have the same image by F in sets, so that it is irrelevant to search for any inverse factor. Yet, it admits a left adjoint from sets to AB, obviously, namely the free factor F, which associates, it is a free factor which is the left adjoint. I note this construction of free groups, they had been for long rather a marginal issue, had found a fundamental new part in homology and became capital in categorical adjointness. Exactly in the same way, the diagonal factor delta, for instance, from sets to set cross sets, which associates to each set the pair E, E, to each set E the pair E, E of sets, cannot be thought of as onto. Not every object in set cross sets can be got in such way. Yet, delta admits a right adjoint, namely the functor P of direct product. This is the proof. The same diagonal functor admits a left adjoint, namely the coproduct factor, meaning here, in the case of sets, disjoint union. This is the proof. One can then extend to any other category the construction of product and coproduct, if they exist, as right and left adjoints to the diagonal factor. Consequently, product and coproduct can be completely defined with adjointness. I repeat, actually, the ancient figure of thought by equivalence has been partly put aside to be replaced by the new categorical adjointness thought. This is a figure of thought, which turned out to be flexible, universal, less restrictive, and became widespread. Actually, Kant's paper was exhaustive. Compare MacLean. Kant took the major step of defining adjoint functors. He then formulated all the related ideas, unit and co-unit. I don't speak of this in time enough. Unit and co-unit of an adjunction existence theorems. Let us have a final remark. The discovery of adjoints seemed yet so important to MacLean that in another text he added, one must pause to ask if there are other basic general notions still to be discovered. The importance, I go on with adjointness and Lauver's hyperdoctrine. The importance of adjointness went increasing along the years. There was even a time for a great temptation of providing in any case one or two adjoints to an arbitrary factor. In particular, in the last chapter of CW, MacLean wrote a development about Kant extensions. He actually decided to support definitely Kant's approach with a striking formula: all concepts are Kant extensions. All concepts had obviously to be understood as all categorical concepts. On the other hand, Lauver's paper in Dialectica 1969, proposed an actual hypothesis of adjointness. His approach, more philosophical than Maclean's, led him to what he called an hyper-doctrine. Lauer's interesting thesis is that the adjunction scheme for two functors was always universally present in the structural thought of mathematicians, consciously or not, I would say. Lauer gave various examples of structuring use of adjunctions, among which, first of all, I will speak of it later, Cartesian closed category, also quantifiers as adjoint, which is an outstanding application, and finally, adjoints expressing Galois connections between partially ordered sets. Here are the first line of Lauer's paper. I said, Dialectica, 1969. The universality of the concept of adjoints. Among the various privileges of adjointness highlighted by Lauer, one will stress exponentiation and Cartesian closed categories. The latter example is important, since it will be a keystone, Cartesian closed category, a keystone in the construction of elementary toposes. For Lauer, a Cartesian closed category can be completely defined in three steps, and by adjunction processes only. First, the existence of a terminal object, then of finite products. Now, no finite products are now, as we know now, no other thing than right adjoint or left adjoint to the diagonal functors. So they can be expressed in adjointness term. And finally, exponentiation, for which I give a transparent quick. Exponentiation means to deconstructualize the construction of A exponent B for two sets of all mappings from B to A, to be deconstructualized and abstracted in arbitrary category if it exists. It's the same, always the same mechanism. One now gives two outstanding, and I won't have time to give completely two outstanding examples of adjunction depicting the epistemological capacity of category theory. Both interpret important works of Stone in the 1935-1940s, previously to the first categorical definitions, with this conclusion. Thou, Stone, raised new and interesting questions. It was actually later on that categorical interpretation could only extract the essence of his discoveries. In Lebesgue's style, one could so say that Stone actually understood what he did less than we do. First example is Stone-Church compactification. Actually, the compactification was made independently and quite simultaneously by Church in 1937 and Stone in 1938 and 1940. There are two papers. 20 years before the invention of adjoint functors. Compactifying an arbitrary topological space does not actually mean making it compact, but finding, if possible, a compact space key together with an embedding E from X to K in order that E of X be dense in K. One usually identifies X with E of X and considers X as a subspace of K. This is not, however, always possible, and Stone recalled in this text, in the first text, 1938, that a necessary and sufficient condition of possibility is that X satisfies a certain strong enough separation property. Laurent Schwartz explains that one actually requested a sufficient amount of continuous functions, and be therefore X called a so-called completely regular space. Actually, Stone elaborated a specific type. C'est le droit fil de la pensée de Stone. Stone elaborated a specific type of maximal compactification in which X is embedded in such a way that every bounded real continuous function on X can be extended to a continuous function to the compactification K. It must then be unique. Stone's denoted beta of X, such compactified of X, unique up to homeomorphism. The important point for us lies in the interpretation given much later by category theory. Here is, I borrowed a formulation from Johnson, a modern statement of the result. The inclusion, that is a forgetful factor U, from top compact towards top, as the left adjoint B. And the unit of the adjacent X gives beta X is an embedding if and only if X is completely regular. In other words, we have to show this property. In other words, the natural forgetful factor from the compact towards the arbitrary spaces, however trivial and definitely not one-to-one it may seem at a first glance, can always, nevertheless, be lifted up towards an adjoint which must obviously go from the arbitrary spaces towards the compacts and coincides with Stone's compactification as soon as possible, that is, if and only if X is completely regular. Thus, by essence, Stone-Chet compactification is endowed with an actual privilege. It can lift up the forgetful factor. Second example is Stone duality. I shall only give the result and I have no comment. I need only, I shall give only a summary of it. It was actually my next section, philosophical aspect of elementary toposes. Next decisive step was doubtlessly conceptualization and axiomatization of elementary toposes. I shall not develop historical aspects, however interesting they may be. Rather, shall I stress that the concept came from many different and surprisingly distinct sources, from geometry as well as from logic, namely, and first of all, the category Grothendieck topos of all sheaves of sets on a topological space or on a site that is a category equipped with a Grothendieck topology. Another source is a category S of sets as in Lower and ETCS. And a third source is the functor category S exponent S sets exponent C opposite, where C is a small category. This is a category of all contravariant functor from set to small category. Well, I think I will stop there because I just summarize what I shall not say. This is the mechanism of decontextualization. It is which leads to the construction of a subobject classifier. And a subobject classifier is to product, je vais le dire en français. Donc, pour produire le concept de subobject classifier, il a d'abord fallu analyser de façon complète et correcte ce qu'était l'appartenance en termes catégoriques. Et ça se fait par un diagramme de pullback. C'est ce diagramme, donc ce diagramme de pullback fait intervenir une inclusion d'ensemble et une fonction caractéristique. C'est ce qu'il s'agit de décontextualiser. Alors, l'inclusion d'ensemble, ça se décontextualise par un monique. Encore faut-il faire attention, parce qu'il faut l'équivalence de monique, etc. Et on décontextualise également la fonction caractéristique. Le résultat, c'est que sur ce diagramme de pullback, dans lequel on a analysé de façon impeccable ce qu'est l'appartenance ensembliste, et on comprend à ce moment-là que le 0,1 qui figure dans le diagramme, on comprend à quel point rétrospectivement la pensée ensembliste est directement associée à la logique binaire, eh bien on fait un shift sur le diagramme en remplaçant donc l'ensemble à deux éléments qui est 0,1, en un premier temps, roughly speaking, par un ensemble oméga qui contient 1, auquel on demande ensuite des propriétés supplémentaires. Donc, ce sur quoi je voudrais insister, excusez-moi si je parle français à la fin parce que j'ai plus le temps, ce sur quoi je voudrais insister, c'est la procédure de décontextualisation, qui est une procédure constante, mais qui s'appuie sur une première analyse. C'est it does not go without saying. The categorical structure to extract from a set theoretic concept. Voilà. En français, René, s'il te plaît.
Oui. Ça marche pas, hein. Gottfried. Ça marche. Alors, oui, la décontextualisation, en effet, c'est une bonne ressource pour l'analyse épistémologique de ces situations. Il y a beaucoup d'exemples qui existent. Alors, je voudrais évoquer, à propos de cet exposé, j'ai eu, ça m'a fait me souvenir de 2 conversations avec Samuel Ellenberg, qui sont en situation, en quelque sorte, par rapport à ce que tu as dit. Alors la première, c'était quand j'avais fait un exposé en 1972 ou 13 sur une version, sur une axiomatisation de la catégorie des ensembles de mon cru, qui était d'ailleurs basée plutôt sur une décontextualisation de la dualité de Stone.
D'accord.
Bon, tout à fait. Et que j'appelais univers algébrique. Alors Samuel Ellenberg était là, et puis après on a eu une conversation assez intéressante sur la méthode d'exposition.
Ah, effectivement.
Et il disait que, bon, oui, l'exposé était intéressant, sûrement. Il s'est pas trop étalé là-dessus, mais qu'il y avait un gros défaut, c'est que j'avais voulu donner trop d'exemples. Et il disait que l'idéal d'une théorie, c'est qu'elle n'ait qu'un exemple, ou du moins que l'exposition soit telle que l'exemple soit identique à la théorie, qu'il y ait une espèce de convergence limite, quoi. Évidemment, c'est un point idéal, quoi. Bon. Alors, je me dis que peut-être il avait là une idée que la décontextualisation maximale, en quelque sorte, hein, parce qu'on a un exemple et puis on essaye de l'axiomatiser, dans un certain sens, mais en tirant tout.
En retirant la substance.
Alors ça, c'est une première remarque. Et puis la deuxième remarque, c'est une autre conversation où il m'expliquait son souci.
Non mais attends, excuse-moi, alors sur ta première remarque, mais que penses-tu de la réflexion d'Ellenberg? Parce que je trouve.
Ce que j'en pense.
Oui.
Parce que toi tu en penses.
Je trouve étrange le fait Bon, j'ai quand même des soucis pédagogiques et je trouve que multiplier les exemples, enfin pas à limite, mais des exemples de nature différente qui montrent comment fonctionne ou ne fonctionne pas un procédé ne fonctionne pas aussi. Une procédure de décontextualisation, c'est tout à fait essentiel pour cerner la genèse d'une méthode. Donc je ne suis pas d'accord avec ce qu'il dit.
C'est une question d'idéalité.
Pardon ?
C'était une question d'atteindre un idéal.
D'accord.
Je donne tout de suite la deuxième.
Oui, bien sûr.
La deuxième chose, c'est sur la question des noms, parce que tu as dit que c'est lui qui a donné le nom d'adjonction.
Oui.
Il l'a suggéré à Kahn, comme le mot adjonction. Et ça aussi, il avait un grand souci des noms, puisqu'il racontait souvent que pour les suites exactes qu'il a introduites dans leur généralité avec Steenrod, ils ont fait exprès pendant une année d'appeler ça des black séquences, tant qu'ils n'avaient pas trouvé le bon nom, de manière à ce qu'il n'y ait pas un mauvais nom qui se glisse dans la mathématique. Ils avaient de noms en réserve comme ça.
Ça, c'est un souci que je trouve extrêmement louable. Moi, par contre, sur le terme adjonction, j'aurais quand même une réserve, c'est qu'il renvoie à l'adjoint d'un opérateur linéaire, par exemple dans un espace pré-hilbertien séparé, et qu'on n'a pas le même type c'est pas ressenti de la même façon, si tu veux. Le relever un foncteur par un foncteur à droite ou un foncteur à gauche, c'est pas la même chose que de prendre l'adjoint d'un opérateur dans un espace d'un opérateur linéaire dans un espace de Hilbert. Alors, le fait que Stone est omniprésent, omniprésent après sa mort, enfin après sa mort, disons, après qu'il ait publié ses résultats, 12 ans après, tout ça arrive. Les 2 exemples que je donne, Stone, Chech, compactification, et Stone-Gelfand, etc., traduisent le fait que la pensée de Stone est catégorique. Parce que j'ai travaillé sur Stone, donc je vois, il se pose sans arrêt la question, à savoir, mais que deviennent les morphismes? Et, à ma connaissance, c'est l'un des premiers mathématiciens à se l'être posé, du moins avec autant de constance. Voilà. Merci pour ta question, c'est très intéressant.
D'une part, une petite chose concernant les noms et le fait que MacLean était très soucieux des noms. Pendant très longtemps, on appelle maintenant des monades, on appelait ça des triples.
Oui.
Et puis un triple, c'est un triplé, ça n'allait pas très bien. Je lui ai vendu le mot monade, il l'a accepté tout de suite et il l'a introduit. Il y a des gens qui continuent à appeler ça des triples, mais en tout cas le mot monade est rentré dans le vocabulaire. Bon. Et c'est un mot aussi qui m'était inspiré par des raisons philosophiques, bien sûr. Maintenant, quant à la question des exemples, et que l'idéal serait qu'une théorie n'ait qu'un seul exemple, moi c'est l'idéal inverse. Attends. Mais d'une certaine façon, si on adoptait cet idéal, il n'y aurait qu'une seule catégorie. Les catégories sont justement la chose où il y a des exemples partout.
Et des exemples.
Tout est une catégorie.
Et des exemples radicalement distincts.
Tout est une catégorie. Et c'est ça qui fait la force de la théorie des catégories, c'est que tout rentre comme exemple avec des axiomes supplémentaires, mais de la notion de catégorie. Donc, personnellement, moi, je pense que, bien sûr, avoir une théorie à un seul exemple, mais alors pourquoi une théorie? Il n'y a qu'à travailler sur l'exemple. Mais au contraire, avoir une théorie qui fonctionne, je dis bien qui fonctionne, qui permette de prouver plein de théorèmes, mais qui ait un grand nombre d'exemples, c'est justement une économie de pensée tout à fait extraordinaire.
Mais moi je suis...
Parce qu'on traite tous ces exemples à la fois, et en plus on comprend leur rapport, et d'ailleurs c'est pour ça que je parlerai de catégorie et analogie, c'est bien de ça dont il s'agit.
Mais moi je suis d'accord, attends, je réponds. Je suis tout à fait d'accord avec toi dans la mesure où, si tu veux, j'ai essayé de donner dans les exemples que j'appelle des instances concrètes. Il y en a eu bien d'autres, évidemment. Mais j'ai essayé de prendre 4 exemples d'instances concrètes qui détruisent les intuitions immédiates et généralisantes qu'on peut avoir de ce que c'est qu'une catégorie. La catégorie groupe avec un seul élément, avec un seul objet plutôt, et plein de flèches, et une catégorie préordre dans laquelle on a les éléments ne sont pas nécessairement, ils peuvent l'être, hein, sont pas nécessairement des structures, mais tau plus une flèche, voilà, ça détruit, et cette destruction est utile à l'émergence dans les conceptualisations internes, enfin dans la façon dont on fabrique un concept chez nous. Sinon, on travaille toujours avec la même image qui est en gros des ensembles supplemented, enfin en gros avec des catégories abéliennes.
Je ne veux pas monopoliser la parole, mais je vais préciser quand même ce que j'avais compris de ce qu'avait dit Nendian. Il disait que l'idéal est d'avoir dans l'exposition l'opportunité d'exposer un seul exemple, et que ce soit en quelque sorte l'exemple, si vous voulez, l'exemple générique, en quelque sorte, à partir duquel, en fait, on comprend toute la théorie. Mais il ne disait pas, évidemment, que la théorie ne devait avoir qu'un exemple en tant que tel.
C'est justement avec ça que je suis pas d'accord.
Donc, si vous voulez, c'est comme, par exemple, quand on a une théorie quelconque, eh bien, on apprend beaucoup si on construit le topos classifiant, qui est, dans un certain sens, l'exemple. Voilà. Moi, je pense que c'est dans ce sens-là que j'ai compris.
Moi, je reviens à ce sujet, je suis vraiment pas d'accord. Je pense aussi qu'on comprend comment il fait quelque chose quand on comprend comment il ne l'est pas fait.
Just would like probably support that point of view. Correspond what I tried to say yesterday, what René is talking, because I think, of course, it still works in category theory, this kind of, I don't know, what I called yesterday formalization, but probably also quite linked to generalization. When we say category, everything is category, like groups, topological space, so on and so on. But I think it's in certain sense, probably it's not what, how to say, what is the specific about category theory. What I mean, probably it's kind of, I don't know, condition could be for, I don't know, for making factorial links between different theories. But on the other hand, we can probably regard functor, you know, as in the remark mentioned you by Maclay and later by Fred, is kind of, you know, basic notion, which would mean that before we're making categories like common form of topological spaces and whatever, we just make kind of functors between objects and regard that functor as, you know, kind of primitive. Mm-hmm. And actually my question, before I give to Charles, link to that, it's about that remark, right, that the very notion of categories is elementary.
Je voudrais juste dire un mot sur ce que tu dis, savoir que dans l'histoire des mathématiques, il est peu d'exemples d'une axiomatisation, enfin, aussi simple, parce que l'axiomatique d'une catégorie, c'est quelque chose d'extrêmement simple, qui soit né dans un contexte qui soit quand même aussi relativement compliqué. Et c'est ce que j'ai voulu dire en disant à un moment que s'il n'y avait eu comme exemple, s'il y avait comme motivation que d'expliquer l'homéomorphisme X croix Y croix Z, etc., et fabriquer une théorie pour ça, on aurait rayonné déjà, enfin, une chose pareille, c'est pas la peine. Donc, c'est, parce que, autrement dit, la simplicité de l'exemple, pour en venir, décourage l'inventivité. Donc, il a fallu, pour qu'une théorie avec une axiomatique simple naisse, un problème relativement compliqué, pas tellement compliqué, j'ai essayé de le dire, pas tellement compliqué à comprendre, mais compliqué à communiquer. Et ça, c'est la même leçon que celle du XVIIe siècle, c'est-à-dire au moment de la création de l'écriture symbolique mathématique. Il ne s'agissait pas de problèmes qui étaient en soi compliqués, mais qui étaient difficiles à communiquer à l'autre.
Actually, this question of mine is whether this vision, right, that basic notions, category theory, functor and nature transformation, whether they comply, say, with this category of categories approach, which probably historically dominated later, right? And because there are a lot of things about that remark. First, obvious that unless we coming to functor nature transformation, the whole theory is trivial. And second thing, that it's kind of closure. It's like, you know, in set theory, Cantor distinguish, say, elements and sets as kind of types, and in Zermelo-Fraenkel theory we have, you know, the universe of sets. Elements are also always sets, and that kind of conceptual closure. But on the other hand, of course, functor categories are categories, so somehow they become in the categories of categories. But on the other hand, functors as objects is rather specific object, like they're not identities. It's not just a question to dispense with objects, replacing them by identities errors. I just wonder whether this approach really realized.
Well, I'm not sure that I understood completely what you mean. A functor category is a conceptualization of a second level. Well, it is usual in mathematics. En analyse fonctionnelle, les objets, c'est les fonctions, et la difficulté conceptuelle qu'il y a à faire passer à ça aux étudiants, lorsqu'on envoie une application d'un espace de fonction vers un autre espace de fonction, il y a un saut parce que préalablement, les espaces de base avaient été virtuellement considérés comme étant des espaces géométriques. Il y a des étudiants qui ne suivent pas ça. À ce moment-là, il y a quelque chose qu'on doit expliquer. Bon, c'est me semble-t-il la même chose avec les...
Oui, juste...
En français, hein.
Oui. Juste deux petites questions sur votre superbe reconstruction de la saga diagrammatique. À propos du diagramme comme guide for thought, comme guide pour la pensée, vous avez soulevé le problème de ce que c'était un pragmatisme initial de l'approche de Maclay. Est-ce que vous pensez est-ce que vous savez s'il y avait un lien quelconque ou si Maclay se réfère quelque part aux travaux de Peirce sur le diagramme justement et sur l'approche pragmatique?
Je ne suis pas très historien là-dessus. Je ne crois pas, je pense que Colin pourra répondre mieux que moi, je ne crois pas. Les seules indications historiques qui sont dans les notes historiques du CW, à la fin, elles sont pas mal, hein, il y en a à la fin de chaque chapitre. donne, me semble-t-il, l'origine. La flèche est quand même un élément essentiel. Hein. C'est Hurewicz qui l'aurait pour le premier utilisé, mais les diagrammes, je ne crois pas. J'ai tenté d'expliquer que la complexité, entre guillemets, parce que c'est pas tellement complexe, mais c'est simplement vraiment difficile à expliquer si vous voulez l'utiliser avec l'écriture symbolique. Je répète, c'est le même problème que le XVIIe siècle. Hein. On pourrait, en droit, on pourrait, mais en fait, on le fait pas parce que c'est compliqué. Et expliquer tout simplement le shift d'une short exact sequence under a chain transformation, il n'y a pas beaucoup d'éléments, on pourrait y arriver, mais c'est tellement plus illuminating de l'expliquer comme ça que MacLean que Ellenberg et MacLean l'ont introduit. Je crois qu'il y a, sauf erreur de ma part, hein, je ne suis pas historien encore, je crois qu'il ne doit pas chercher autre chose. Il dit que la flèche, c'est pas de lui, hein, il dit que c'est Hurewicz, etc. Mais vous vous rendez compte que le papier de 42 n'utilise aucun diagramme fléché de short exact sequence. Hein. Même pas linéaire. Hein.
Ouais. Et la deuxième question, c'est avant que Ellenberg suggère le mot qui est devenu le concept d'adjoint, est-ce que vous savez comment était dénoté le concept d'adjoint avant?
Ah mais c'est venu en même temps. C'est venu en même temps parce que Kahn passait à la Columbia et il a... Non, ça a été à la fois la chose et le nom. Oui.
D'accord. Merci.
Je crois que c'est le pro adjoint. Et après, c'est pro et laissé tomber.
C'est vrai que une des propriétés caractéristiques de la théorie des catégories, c'est la flexibilité, c'est-à-dire la multiplicité d'interprétations et c'est vrai aussi, c'était vrai aussi pour la notion de groupe. C'est une propriété qui n'est pas arrivée dans la pensée mathématique avec la notion de catégorie. C'était vrai. Le problème même de avoir une théorie catégorique dans le sens de la théorie des modèles, c'est-à-dire une théorie qui admet seulement un modèle au moins d'isomorphisme, était présent dans la correspondance entre Frege et Hilbert au début du XXe siècle, parce que Frege demandait de la géométrie l'existence d'un modèle, et c'était une condition de signifier.
Attendez, excusez-moi, vous prenez catégorique là dans le sens qui n'admet qu'un modèle, hein?
Oui.
Oui, bon, d'accord.
Oui, je parle de...
D'accord, non, mais c'est
Hilbert,
beaucoup de catégories.
Oui, c'est ce que Jean Benabou disait, c'était que la théorie des catégoriques est le principal exemple des théories non catégoriques. Oui. Hilbert objectait à Frege que le meilleur complément qu'on peut faire en théorie mathématique, c'est d'avoir beaucoup de modèles.
Oui, mais je sais, c'était complètement contre la pensée profonde de Frege. La pensée profonde de Frege était catégorique au sens philosophique du terme.
Oui.
Les axiomatiques...
C'était catégorique dans le sens de la théorie des modèles. Il voulait que
Oui,
l'axiomatisation...
D'accord.
Alors, what is added to has to be added to Hilbert's reply to Frege is not just the multiplicity of models, but the existence of generic models. Because generic models, that is which is connected to the essential presence of joints in construction of models of any theory.
Yeah, je suis d'accord. C'est un beau programme, hein, mais il faut se mettre en face d'un problème et de voir comment. Oui.
Ou sinon,
est-ce qu'il y a une relation connue entre les adjoints comme historiques et puis les correspondances de Galois
Oui,
qui sont avant, et qui sortent.
Oui, oui,
Est-ce qu'il y en a un l'un que l'autre explicitement?
Enfin, chez Lovir, il y a une. Bon, tu trouveras dans le. Ah, chez Cannes, non, je crois pas. Ça, je te dis, je t'affirme pas. Mais c'est Lovir qui le met en valeur, et tu trouves une présentation moderne dans le MacLean Sheaves in Geometry Logic de ça. Tu parlais du point de vue historique. J'ai pas lu le papier de Cannes jusqu'au bout. J'ai regardé quels étaient ses présupposés, et c'est très clair. Hein, comment il met ça en œuvre, mais je l'ai pas lu entièrement. Non.